Hello everyone, welcome to another session of Code with Your Friend. So in our past session, we started converting the C APIs that we had written for all the Java linked list interface APIs that we could figure out from the web. So all of those APIs we are converting to LL macros. So LL macros, just for some context, are some of the macros which are defined within this utilist.h file, which is written by Troy T. Hansen, and it's an extremely good utility for using linked list in C. So far, we are only starting to scratch the surface of it. We are only exploring single linked list, and I have found this new macro expansion technique very funny because I haven't used this inlining feature much in my prior experience. So yeah, I'm converting everything possible to macros just to have fun around it. I know it's not the right thing to do, but because one solution should not fit all the problems, and but this is just for exploring this particular method, how powerful it can be. And since it's my personal project, I'm free to do whatever I want, and I'm putting this constraint to move all the APIs that we have in C to use the LL macros. And let's see how much we are able to convert here. Um, let's get started. So we have already converted few macros, few functions here. Let's go to this. So it's basically add index. So add index, I don't think there is any indexing APIs that's defined for linked list, which is actually right. Java uh, had that index thing because if we have an array and linked list mapping, sometimes it's useful. For example, we have created an add all function where we are adding all the array elements into a linked list. And let's say we are modifying some element in the index in array, we might want to do something with a similar index in linked list. So probably we would need that. But again, I think let's just look at the purpose of it. So add index, what it does, if it has a linked list, it'll try to insert an element at a particular index. So I think that's I think the utility what it did. It might be a little bit complicated. So let's get started with that. What are the things we have here? So we have I believe we have a comparator function, but that is like element comparison. We expect maybe sorting within the linked list. That kind of thing is useful. We have usual append, we have usual prepend, but we don't have in an indexing concept. So that's something probably we need to figure out how we can do. Um, I think the add index could be like we could specify an index, um, and the macros typically don't have that much of error guarantees because we can write a macro like that because if it expands, it should have some kind of error check, but we don't guarantee states or guarantee success or failure by some return values. So that return statement thing won't mean anything here. So either it would do what it does or it won't. Uh, and it should just exit. Maybe we can set some values of a variable um, if we really want to do in that way, but that's really pushing the boundaries. Um, but probably we can do that. I'm not sure if it's actually right to do that kind of thing, but let's see. So we have new, we can. So we have to basically iterate the elements. There is something similar which is like LL count, which counts the elements there. and it's just in um, I think what we can probably do is we can create the element outside and using the value that is passed. If indexed is, and we can also figure out maybe the count of element in the list. If the count of element is, we can figure out the count of element, and if the count of element is, or if the index passed is within between 0 and count of element, then we can do stuff, otherwise we can't. That kind of check we can probably put in so we properly set those error conditions. Otherwise, these kind of specific things do we need to do. Uh, this can be easily replaced with prepending, basically. So if we find, then so let's actually do this thing, right? So what we would do is we can just find an index. So before add index, let's see if we can implement find index. If we can find an index, for example, um, index of is actually still value, but if we can find, let's say, ith element, then we can just do a prepend of that, and getting that ith element will be quite useful. So let's see if I can define something like um, ll find index. So I have this list. The thought process is a little bit different because we are not passing to a function, we are just doing inline processing. So that will be a little bit tricky. And index will be, let's say, will be already defined some index which we need to find. And what we would do here is while head is, and we are going to modify head, right? So let's say, I think we should do an ll for each here. For each head e um, and let's say here we do something, we also increment the value. What we can probably check out is utilist.h. How do they implement the count? That should give us some. So basically, if we pass the counter, for each just increment the counter, right? Um, Similarly, we can do probably. Let's see if I can at least find the ith element. So I can just increment this counter and if, and I also need to pass a counter here. So counter should be there and then the index should be there. So if counter is equal to index, then we'll just break, and we need to increment the counter and this should do, right? So then the find index should be here in E. So let's say here I do ll find index head1 e counter is I and I see third index element, right? If something is there in E, then just print it. What is there? %d \n e name. Sorry, so it should be %name. So E is not null, it seems like. The reason that is happening is because we are not incrementing E, right? So ll for each, what is it doing? ll for each, it's here only. So we have E which is assigned to head, and then until that happens. So this actually can't happen for this, right? So actually it's not ll for each we should do here. Probably we can just have the counter here. Let's make it counter. Let's make it simplified. So counter is less than index and counter plus plus, and we'll start with he gets assigned to head, and yeah, we can wrap it, and yeah, well, and then we can have points to next. So the third element, we found it, right? So this is the way we find the find index third element, and now we want to add an element at an index. So let's say if we find this element and now we just create another element. Create element. Do we have another pointer here? Let's just put e1. So we can put e1 and something like name6 and an ll prepend, right? ll prepend head1. But actually ll prepend element. ll prepend element is head1. Then what we have, reference and then add. So reference is re, then add is e1, right? Then just we do print all. How about that? So this sort of works, right? And which means now if I can just do hash define ll add index head e counter index. I think that's it all. So this will just do head e counter index. It will find the index, then we'll just do ll prepend element head E, and we also need to send what is the value that's actually we're sending here. So we'll just ll create element. You can send everything here. It's like it can do everything. I will just add this, and I'll add this also. And then this entire thing converts to ll add index, where you have head, and then you pass e, then you pass an index I, then you have, let's say 3, then you have 1, and then you have a value, let's say name 6. Cool. So this is cool, but this is insanely unreadable. It is insanely compact because just look at it. I mean, we are actually skipping a lot of the error scenarios. So, but even within that, this function, which has around like 30, 35, around 35 lines, then we are just compressing it into 4 lines. And eventually, I think the find index also contributes maybe 8 lines. So we are finding the index, we are creating an element, and we are just depending the element of that. There are a few error scenarios probably we can mark it if we need. Probably, let's say, so I think we can assume, at least for this particular case, because we're not creating like production ready code, that at least for the valid scenarios, the index should work. But if we are creating, if we want to expose the APIs where we should have the bound checks stuff, then probably we should do thorough checks even there. In fact, we can also do some thorough checks here. For example, we can check if index falls within 0 and count. That's, I think, one of the good checks that will be there. If head is null, will that actually impact? So we won't find an index there, so E will be null. And if head is null, what would happen? So our find index, this thing actually will crash because we will try to increment till that point unless we specify, like this is the first element that I want to include here. Let's actually hypothetically try this, right? So let's say we don't add all and just we do an add index. So head 1 is null. So I know I want to index at 0, and I just provide name 7 there. Do I hit a segfault? I don't, but do I insert properly? I do. So it seems to work fine. Even I think if we, let's say, continue to do that, that essentially becomes like prepending, right? So we are just prepending elements. So this is actually covered. So head is null, that is covered. The only part that is not covered is the index check. So the index should be proper. Otherwise, it should not work. For that, let me just take a look at how the list hash, does it have any kind of check, or is it just like a boundary scenario. So I don't think so. This is a very tight library. It does not have that kind of a scenario. If you allow like indexing on linked list, um, you're essentially creating a loophole in that, right? Because just move the camera a little bit. Oops. Okay. Yeah, essentially, if you're creating an indexing structure on linked list, and if we don't provide a correct index, then we can possibly run into array index of bound exceptions. So one way we can probably see is error exit error in C. I just want to exit the program. So exit function expects an integer value. Cause normal process termination, and let's see. Okay. So we can do an exit 0 and exit success, exit failure. We can just do a printf error, C printf error. Something like this. So we can possibly try out this, right? Let's say if we provide this and under what scenario it will happen if E is null, right? So if E if not E, then right. We have to do something right. So I'm bringing the Java pattern in C, which is weird, but index out of bounds. Exit failure. Um, does it compile? Does it run? What if once it happens, I say I want to accept this index out of bounds, but it does not say why it's index out of bound. But it actually handles that error. So I think this error condition is not really friendly, but at least it handles it in some way. But yeah, otherwise this add index works perfectly. So if I don't have this, it works fine. If I just do an add all on top, what would happen? Oh, okay, yeah, I should have. So after we add a bunch of these things and then we again try to. This is amazing. So everything works Index of. So index of is kind of reverse thing. Um, we probably have the search function there, and we essentially want to find an index of an element. So, oh, essentially, yeah, find index. So find index. So that's actually find index, but it's not essentially index of an element. So if you want to find an index of an element, so the search function gives me the exact location. This is like an indirect way of getting that. So I think we can modify the search function a bit. So if we look at ll search scalar, so for each it just compares and kind of an infinite loop. Um, so the search function basically works by doing a for each and then breaking out of it. Um, so find index is that, add index is that. So we can do like a similar. I mean we cannot use a structure, similar structure, but I mean we can't reuse any of these. Um, Maybe lower bound, but that indexing thing is actually problematic. So we have to write something our own, sort of like a search function. So ll index of, then we have head e, then the counter index we don't need, and val. What we can do here is basically we can just yeah, we can just directly do the for each break is fine, right? So yeah, something similar I can do here. It's within a do while block. Do while false. Do false, right? Why is it within a do while false? If we put something in a do while false, do we not need this? Is that a hack kind of? I don't know. I mean, I don't think we don't need a do while false here, but we can reuse the for each. So ll for each if e name is equals val, then break, otherwise we'll include increment the counter. Just I think for exploration, if I wrap this entire thing into while 0 statement, I don't know, I don't think I'm getting what I'm expecting, but anyway, it's not required, so that is fine. So we have to just put these here. Right, and the counter should have, it can also be called index. If we don't have index, then index is equal to count. So ll index of head1 e, and also I guess index should be initialized to 0, right? I and say name 6. $49. %d \n index 3. So it's retrieving index of properly. So let's just add this guy. So ll and index is here. Ll index of is here. Get first. Get first should be fine, right? So get first is essentially get first is just the head element, the first element. How can we get first? So we already have the heads reference. So what does that mean? Just assign that value to a character pointer or something. Could be a null also. And then get first. We have a head and then destination. Call it val dest. And then we have val dest is equal to if not head, then you have val dest is equal to head name. Something like that. If I have like character pointer test and I will get first. This is just like forcefully trading APIs. Those APIs, no one will use them. Just if test. x86 64. What? What does this do? This is like expands to this, right? If not head 1, then and then print resuming after a break. So I think the part where I left was we were trying to just get the first element. It seemed it would have been an easy option, but turns out it's actually tricky. So what I'm doing is I'm passing these options, destination, and I'm just doing a string copy. So let me see string copy, how to properly do string copy. So we should have some buffer, right? Then it becomes easier to do something like this. Okay, so the last one is actually working. The first one is not. And can just say something like this, invalid initializer. What about so now we are not printing anything when it's null, otherwise we are printing the first. Yeah, I think this is fine. So we have got LL get first here. Similarly, we want to have get last. How do we get last? I think basically we have to traverse. So let's just traverse it, and we can use that same for each function. But yeah, let's experiment. Get last. So I've got head 1 and LL for each head E, and if E next is null, then break. ll get last, head 1. Identify null is undefined. Next. So we've got name 5. This is the last element, which is right. Awesome. So we have also got implemented get last, remove first. So there is an option to do a delete. So hash define ll remove first. So what basically I need is in fact the get first should be so get first and get last is different because in get first and ideally it should just return the it should be called like get first val or something. Because essentially get first is your head pointer itself. There is no reason to have another get first, just a copy of head pointer. So remove first is you want to delete the first element itself. Let's see. Can I do something right? Head and head. What will happen then? Cool. It's working. So remove first is just ll head and head. This is so remove last. I think here we will probably need E because we need to figure out what the last element is. We'll just do we'll get last head E, and then I'll delete head E. So name 5 should be deleted. Possibly as well. name file is deleted, so that's also working fine. Contains contains, so it should return 1 or 0, something like that. um ll contains head, and it should be a val. So what we will do is do an ll create element with val, and after that we'll just do ll search out. What is ll search as sort search scalar. ll search head, result the name CMP. If this is not null, then it should be something. ll search operation is shortcut for particular element. Scalar version simple equality test. Algorithm version takes an element which all others compare to a function. This and output. Okay. So ll contains. So ll contains. I think this is also. I don't think we even need this kind of thing, right? So the scalar operation is already there. You can just call the. It can be just a scalar, right? If it returns something. So got head one, the outfield, that field is name, val is name, temp, if e. So it's not there. No it prints. The search scalar should be size. Size is exactly the same as count, so we don't need anything. Remove val. Remove val. Yeah. So we can call something like remove val head val search scalar head e name comparison. If e, then delete head e. Scalar. This is okay. Yeah, I mean, I have to remember to print this. Name point is gone. So I think we are almost near the end. And I'll clear and then for each safe, I think we need to pass these head e tmp. So it's just empty. Everything's cleared. So we have LL clear. Last two. So I think we'll just try to finish them off in this video itself. Then we can sort of move away from the single list part. Last index off. Find index. Actually, this is something similar that we can implement. Do this, and then what do I have inside? Hello for each, right? And the inside we go like and we also need an index. Also need an index, we also need a counter. If okay, then I think we I guess if we have that, it's better. But yeah, we don't need it because we can directly start comparing. Right? It's a scalar comparison. The API is not very clean because we are not, I mean, there is a bunch of scope for cleanup. So let's see. I think let's see if it actually it's gonna be a long thing. E1, we don't need E1, so one less head E value counter an index. Head E values, let's say name 4, 5, and index. Didn't work, huh? Because we did a clear. Oh, 7. Wow, should not be that right. E. So it should be less than 5. How can this be? So in for each, okay, yeah, it will depend, I think. So we have to initialize the counter to 0. Um, 0, 1, 2, 3, 4. Makes sense. So last index of is also done. Clone. Clone should be quite simplified. So we can do ll clone head. Let's call it destination. Probably as well. ll for each head 3. ll bend destination. This stage and do ll clone of head 1 e 2 ll print on 2 e. What is the issue with that? Expected here. Okay, so I think the problem is um, I think we should probably append element or what do we have here? Can have an add all, but that's actually for an array. I think it should have worked. Let's see what the expanding version looks like. Why? This is fine, right? Two few arguments. So this expands to, for this, we're going to do this type of next is null. If head to, then head to, while then next and next head to is equal to e. So I believe if we just do for each save, for which we have to pass in a temp, it's better. Now I think it's fine. So because we are modifying. So our last function will be ll clone. So let's quick do a recap. With this, we have created corresponding LL equivalent for all the APIs, and now I think we are quite confident of using the LL functions, right? Um, but we have to still see the DL functions. We have to still see the CDL functions, and then there are a bunch of a lot of other things which this library provides. Anyway, so I think so today I'll just do a, let me do my git push. Complete C linked list APIs using LL macros. So now I think, yep. So I've pushed this code to my repo, and I'll put the link to this commit in the video description. That's today's work. Thanks everyone for joining. See you in the next session. Bye bye.